Okay, the next thing that we're going to be talking about is phase transitions. You guys know what I mean by phase transitions, right? Yes, no, maybe?
No.
No.
No, you don't remember the phases?
So it's solid to liquid to gases. You're going from one state to another.
Oh,
okay.
Gotcha.
Yeah. Okay, so that's going to be the first thing that we're going to talk about. Then we're going to kind of break it down. I'm going to give you the definitions, some general definitions of phase transitions. And then we're going to talk about how the phase transition relates to the intermolecular forces. And then we're going to talk about heating and cooling curves, okay? And some of the stuff you guys have already done before when we did thermochemistry. So it'll be a recap. Okay, so when we talk about phase transitions, you guys know that the general stages, the general phases, solid, liquids, and gas, right? So when you go from a solid to a liquid, right? That's melting, right? That process is melting. We also call that fusion, okay? When we go from a liquid to a solid, we call that freezing, right? Yeah, no, maybe?
Mm-hmm.
Good. Okay, so when we go from a liquid to a gas, we either say that's evaporation, or we could say it's vaporization, okay? When we go from a gas back down to a liquid, that's condensation, okay? So when you see the water condensing on the cup, right? So that's actually water that is coming from the air, you know, and it's condensing on that the cup of juice you have or whatever you have, you know. So when we go from a solid to a gas, that's called sublimation. When we go from a gas to a solid, that's called deposition. Okay. Now, these processes, they get into equilibrium. So when you get to the point, there's a point where you reach dynamic equilibrium where you have, let's say we have water and vapor, right? So the arrows here going both directions, there's a point of equilibrium that is established. So that is actually called dynamic equilibrium. And so what that basically means is that let's say we have just a pool of water, a lake or something like that, right? So on that lake, there's vapor pressure above it, above water vapor pressure above it. And then there's also, and then of course there's the water in the lake itself, right? So the rate which the liquid is vaporizing and the rate which the liquid is, the gas is condensing is going to reach a point of equilibrium. So basically they're going to be going exactly the same speed in both directions. Does that make sense? How can I say this another way? Okay, so that word equilibrium basically means coming to equal, becoming equal, right? So again, if I have, this is my lake. So there's going to be vapor being produced. And then there's going to be, from the vapor, there's going to be water coming down, okay? So overall, there's going to be an equilibrium established between the lake and the air that has the water in it as well, so that the rate is going to be consistent. Because if it isn't consistent, then that lake will disappear. Does it make sense? Like, for instance, if you guys go out here in the summer to, where is it? The Kings River. You guys seen the Kings River when they open the dams and everything like that?
Yes.
Okay, so basically what happens is that the Kings River, if the environment is conducing, the Kings River will actually get into a form of equilibrium. So you'll have the same level of liquid during that entire point for a long while, right? But if it gets too hot, what happens is it changes that rate, right? So then, in other words, the temperature will cause that equilibrium to shift, right? And causing it so that you'll have more stuff that's coming up than going down. But ideally, if given enough time, if the right temperature, let's say room temperature or something like that exists, then you're going to have equilibrium established where the vapor that's being generated and the liquid that's being generated are going to be equal. So then the level of the lake doesn't change. So like in somewhere that's a little cooler or something like that, those lakes don't drop. They don't drop too far, right? Because the weather is more stable than it is here, where we go through like extremes, really, really hot summers, and then not really cold winters, but cool winters, right? And so like, let's say, for instance, in the early spring, if we had a lake, the lake would be pretty consistent in terms of the level. So one wouldn't be more than the other. So you'd have equilibrium established so that your rate is going up is also going down. Does that make sense?
Yeah, I think I got you.
Okay. Okay, so basically, when you have a closed system, your system is basically going to it's going to reach a level of equilibrium. I'm going to show you that here in a second. Okay, so again, vapor pressure, basically it's going to be the number of molecules or the rate that the gas is going up compared to the rate that is going down. So overall, the number of molecules, when equilibrium is reached, there should be no change in the number of molecules because they should be exactly equal to each other, right? But what is going up should equal to what's going down. So there should be a total of 0 change if you're in equilibrium, okay? And that's going to be important because we're going to be talking about equilibrium pretty much the rest of the semester. So you want to get that in your head right now, what equilibrium means, okay? Now, vapor pressure is directly influenced by intermolecular forces. You know, you can't get away from it. When in doubt, the answer is, Jessica?
Intermolecular forces.
Intermolecular forces. Okay, now we're going to look at an example of that here in a second. And I want you guys to sit there and use your heads, think about it, think about what you guys already know. Try to figure out the next problem that's going to be coming up. Okay, so again, vapor pressure is just the vapor pressure. It's the pressure of the vapor at equilibrium when we're at equilibrium on the liquid. Okay, so here if we have a liquid in, let's say, a closed environment. So this is a closed container. So as we first put the liquid in there, and let's say this is our mercury that's going to be determining our pressure, right? So when we first put the liquid in there, there's going to be like a minimal pressure that's going to exist, right? Over time, as we let that liquid sit and sit, it's going to reach equilibrium. And you're going to notice that the pressure inside the container is actually going to increase because it's getting to a chance to become in equilibrium. And then eventually it's going to reach the point, its ideal point of equilibrium. And then, so then you'd be able to determine the pressure. Okay, so when you're no longer noticing any changes, that's when you have reached equilibrium and you're able to analyze your pressure at that point. Okay, now basically what that means is that the vapor, the rate of vaporization is going to be equal to the rate of condensation. And so they're going to be equal to each other. Okay. And then at that point, that vapor pressure is going to be a constant when it's at equilibrium. Okay. So it's not going to change for a given specific. Okay. Questions, concerns, Cash, you got it? Understand that?
I think so, yeah.
Okay. So, oops. Sorry, got carried away and forgot to do something with that slide. Okay. Okay, so given the structural formulas of these four compounds, explain their relative vapor pressure in terms of types and extents of intermolecular forces, IMFs. Okay. So let's see, there's 8 of you guys. So really there's 7 of you guys, 6 of you guys, not including Jessica. Jessica, do you want to participate with this? Yes or no? No? Okay. So I'm going to put you guys in groups and I want you guys to discuss it. Each of the different molecules, you got a picture of the molecules?
No, I do.
Yeah, you do. Okay, good. So, and I'm going to come in and check up on you. I'm going to give you guys 10 minutes. 10 minutes good to discuss it?
Yeah, that's fine.
Got some answers?
About that. We
What do you mean by about that?
But I don't know.
We can tell you what we thought.
Well,
Yeah.
that's exactly what I want you guys to do, right? Right now, this is a thought process. I want you guys to think about it. Tell me what you thought. Okay, group one.
Who's that?
Group one would be Abby, Matt, Alberto. And then group two is Cassie, Kayla, and Sadie and Selena.
Okay.
Okay, so in other words, okay, so let's start off by putting them in order of who do you think is going to have the highest vapor pressure and who's going to have the lowest vapor pressure. Let's do it like that. Let's start off with that.
So we definitely agree that the lowest would be water.
Okay. So you say, well, okay, so do me a favor, put the order that you think it is. Abby, your group. So okay. Group one and then group two. And let's see who's the most accurate.
Okay, let's see if my team agrees with me or not. Selena or Kayla, do you want to take point for us or?
And let's put a little wager here, like make it a little more interesting.
No, right? No wager.
What? We all like each other. Don't make us.
No wager. Right off the bat, no wager. I'm stopping my order.
So let me tell you what the wager is first, and then you can tell me if there's no deal or deal.
Okay. You're giving us money.
No money, no money.
Oh, dang.
Points. How about a few extra credit points? Extra credit points.
Oh, no.
So for the group that gets it the most correct.
Okay, I don't know. No, actually, no, I don't know. We all get along. I think we all deserve the points.
No. It's a competition, you know?
I don't know. What does the other class say? I mean, like, class, please speak up. What do you guys say? Yes or no?
So 2 extra credit points for the group that gets it the most correct. Yes, you got to keep track of the points. You got to put it down there. For the group that gets it most correct, is that a deal? You guys up for it? Because I have like 4 example problems for this section right here. So this is one.
Oh.
I mean, yeah, I'm up for it.
You're up for it? Okay, so both groups put the order that you think it is, and then we'll go through your explanations. Okay? It'll take you a minute, hot minute. Put it up.
Matt, send me a message through the chat just to me so you can. What were the other 2 that we also said we're gonna go? Hold on.
Dr. Henry, there shouldn't be a problem for Cassie. You should see her in tutoring.
Oh, yeah.
Oh, you done threw me under the bus, Jess. What was that about?
Okay, let me annotate.
Also going to remind them about their practice tests.
Oh yeah. Oops, sorry. So you guys, your practice test is going to go up tomorrow morning. It's a day behind. Your exam is this Friday. It's going to cover chapters, basically everything that we've done up till chapter 11, because I'm planning to hit 11 on Wednesday. And you guys sort of went over it in class or part of 11, not the full thing, part of 11 on Wednesday.
Dr. Andrew, so we're going from lowest to highest, right?
That is correct.
Okay. Okay, I think we got it.
So that's the order that you guys think the vapor pressure is going to be.
I am not done. I'm almost done.
Sorry, what was that?
I said, I'm just trying to see. Oops. I was trying to. So this is your order from lowest vapor pressure to the highest vapor pressure?
That would be my guess.
Okay. And then this is your guess from lowest to highest?
Yes.
Okay, good. Okay, so we said that intermolecular forces are going to play a part in it. Now let's think about the logic first. So let's just logistically thinking about this, right? So if we take a look at this, so water is able to form hydrogen bonds. Hydrogen bonds are a lot stronger than dispersion forces, right? Because of that, because hydrogen bonds are more stronger than dispersion forces, then they're going to connect stronger. So it's going to be a lot harder to sit there and separate them. So you're going to have less vapor pressure if there's going to be hydrogen bonds involved. So we know that OH allows for that hydrogen bonding. Here, these guys have two OHs as well that allow for hydrogen bonding. And then we have with ethanol, we have this guy here, I should just circle, that are also involved in hydrogen bonding. Now, the dispersionary forces or London forces are basically, when we just inducing dipole, right? So we know that these guys, I'm going to circle those in green, These guys here are going to be really popular in terms of dispersionary forces. And then, of course, you know, the other molecules are capable of doing them. Two polar molecules are able to do them as well, but they're not as important as the hydrogen bond, right? So knowing that now, right? So this guy has hydrogen bonds and dispersionary forces. This guy has hydrogen bond and a dispersionary forces. These guys just basically have dispersionary forces, and this guy has hydrogen bonds primarily. Okay, so which one do you think, now that you know this, now which one do you think is going to have the highest vapor pressure? Right, meaning that it can be separated from each other with really low energy involved.
Wait, what?
Okay, so
You're asking for the lowest or the highest?
Highest vapor pressure.
The ethylene.
Okay, so now think about it. Vapor pressure is going to increase if we have weak forces, right? Because all it is, it takes very little energy to sit there and separate those molecules so that they're not stuck together like in liquid, right? So which one of these possibilities do you think you're going to have to put the least amount of energy in to get the most stuff to separate?
The ether.
The ether, yes. So this guy is going to have the highest vapor pressure.
Oh, see, I thought they were correlated, Jess. Makes sense now.
Inversely proportional, so yeah.
Yeah. Okay.
Okay. Okay, so then who's going to be next?
Would it be the ethanol and then
That's
water?
Right. That is correct. It would be
and
then ethanol, then water, then ethylene glycol.
So then the one that has the lowest would be ethylene glycol.
That's right.
Darn it.
Okay, so let's see. I think group 1 is the most correct here.
Oh my gosh.
And that would be...
That would be me and Alberto and Matt.
That's right. She made sure to let me know, you know. Hey, Jess, did you get that? So you're going to enter that in there, but hide it. Don't let them know that they have that extra credit point. Save it for later.
All right. Alberto, Matt, and who else?
Abby.
And Abby.
Abigail.
Okay. Here. Okay, so now you guys, does that make it a little bit clearer? And you kind of see how those intermolecular forces play a part. The stronger the intermolecular forces are, the more liquid it's going to be, right? The weaker the intermolecular forces, the more vapor you're going to have, right?
Mm-hmm.
Okay. Oops. Did I get carried away? Okay. So, and this is just kind of letting you know that too, right? So if we increase the temperature, we can adjust the vapor pressure, right? The higher the temperature, the more vapor you're going to have, right? So this is an example for water. So at 25 degrees, the vapor pressure is 24 millimeters of mercury, right? But at 50 degrees, it's going to be 92 millimeters of mercury. And that just kind of makes sense generally because we know that PV equals nRT, right? So if we increase the temperature, we're going to increase the pressure, right? And then also, if you think about it in terms of motion and movement, if you're putting energy into that system by adding heat, you're causing the molecules to move faster. right? So then the molecules are moving faster. That means that they're going to have the possibility of breaking away and going into the gas phase, from the liquid phase to the gas phase. Make sense?
Yeah.
Okay. So let me give you a hint, right? Since you guys have a test, if you look at a lot of the stuff that we've done, there's very little calculations. A lot of it is conceptual. Have you noticed?
Yeah.
Okay, so you want to pay attention to that conceptual components. Don't worry about it. We're going to have calculations as well too, but it's going to be primarily conceptual. Okay, so let's see. Okay, boiling points. Now, if we sit there, we think about the boiling points are going to be affected by the same thing, right? The more of those forces that you have, that's going to increase your boiling point, okay? And so if we think about those, the vaporization component too, right? So, so when the vaporization pressure of a liquid increases enough to equal the external pressure of the atmosphere, or the external atmosphere pressure, that's basically when you reach your boiling point, okay? And so that basically lets us know that if we're in an area that has a lot of, or very high atmospheric pressure, right? Like under the ocean, if we go really, 50 feet below sea level or something like that, it's going to have more pressure, right? And if we have more pressure, it's going to take us longer to, or a higher temperature to sit there and reach boiling, right? Where if we're high in the mountains, it's going to take us less temperature to reach boiling. Does that make sense? So like, if we boil water, it's like when you're cooking cakes and stuff like that. If you guys look on a box and they give you the temperature to cook it at, you notice that it says if you're like high elevations, cook at this temperature, right? Yes.
That temperature's always lower, right? The higher elevation is always lower.
Yeah. And that's because the boiling point of things are lower at higher elevations, because you have lower atmospheric pressure. Okay, so it'll boil at a lower temperature. Okay, does that make sense?
Yeah.
Okay. Okay, so since normal atmospheric pressure is 1 atm, right? So then the normal boiling point of a liquid is a temperature where it's above, the pressure is above 1 atm, right? So in other words, you're putting that pressure slightly above 1 atm. That also makes sense, right? So if atmospheric pressure is 1 atm, you reach boiling point when you've exceeded, or you're equal to, the external pressure, atmospheric pressure. If the external atmospheric pressure is 1 atm, you're boiling once you've exceeded that point. Okay, when you're right at that point itself, you're not necessarily boiling. And we'll kind of see that. We'll see that when we show you the heating and cooling curves a little bit. It'll make a little more sense with that. Okay, and so the last thing we've talked about, the heat of formation. Now you know the heat of vaporization. The heat of vaporization, which is also enthalpy, delta H, is just going to be equal to the amount that's required to convert 1 mole of liquid to gas. And then, of course, that's going to be in kJ, in kilojoules per mole. Okay, are you good? Okay, so here we have those same 4 compounds. We have ethanol, ethylene glycol, diethyl ether, and water, right? And so these are the temperature and pressure curves for that. And so you guys can see for ethylene for the diethyl ether, it's a typo, I forgot to put the di part. The diethyl ether, so at 27 pascals, of a pressure of 27 pascals, we're at approximately, what is that, 2 degrees Celsius, right? And you'll notice that, let's say we go up to 100 degrees Pascal. So that's going to be roughly around 38, 36 degrees Celsius. Okay. And so, and we know that 100 degrees kilopascals is basically 1 atm, right? 101. So the boiling point for ethylene glycol is about 37 degrees. The boiling point of ethanol, which is ethylene alcohol, that's ethanol. So that one is just under 80. It's like 79 point something, right? The boiling temperature of water we know is 100 degrees, and then ethylene glycol at 1 atmosphere is even off the chart. So we're not going to see it boil at the temperature scale that we're at. Okay, so again, it just shows us that which one of these had the most molecular forces, the strongest molecular forces, intermolecular forces. Yes, that is true, Jessica.
I'm just putting little side notes as you're teaching.
Yes. So the stronger the molecular forces, the more molecular forces you have, the stronger that they are, your boiling point is going to go up. Make sense? Because we know that the diethyl ether had the least or the weakest intermolecular forces. It just had dispersionary forces. The ethylene or the ethanol had dispersionary forces, and it had hydrogen bonding. Water had primarily hydrogen bonding on both sides, more hydrogen bonding. And then the ethylene glycol basically had a lot of hydrogen bonding and dispersionary forces. Okay, and you can see it's directly proportional in that sense. Does that make sense? Yes, no, maybe? Piece of cake?
Yeah, it makes sense.
Okay, so if you see something that has a lot of OH or FOs and things like that, you know that those are going to form hydrogen bonds. So those are going to be pretty strong, okay? Okay.
Wait, you cut out Dr. Henry. You said OHs and they would form hydrogen bonds and then it cut out.
I said, you know that it's going to be pretty strong, and you know that the boiling points are going to go up. Let's say
okay, I just want to confirm.
Let's say we had a molecule like this. Oops. Trying to think. C. And let's say we're comparing to something that looks like this. Okay, which one would we expect to have the highest boiling point? A, B, let's do this. C.
So A is going to be more, right?
Right. So which one is going to have the highest vapor pressure?
Would that be C? Because
Yeah.
it has the lowest.
It would be a pretty
Cool.
tight
Like
between B and C, right? But C would because B has those hydrogen bonds, which would be a little bit stronger than the dipole of the FOCH3. What was that, Jessica?
Sorry, I got a call.
Oh, okay.
Sorry.
Oh, that's right. Okay. Okay, so so this is basically the Clausius-Clapeyron equation. And so this basically, it correlates the pressure to the heat of vaporization and the temperature that you're at, right? And ln A is basically a constant. And so since we know that this guy is going to be a constant, we can sit there and rearrange our equation based upon P1, P2, and P1 and P2, right? So saying that there are two different pressures and two different temperatures. And then we can sit there and use this to sit there and calculate the changes that would occur between those two pressures and two temperatures. Does that make sense? So let's say, for instance, let's use that. What was the water pressure? Oops. Let's say we have this guy here. Oops. Okay. So if you had this, could you calculate the heat of vaporization?
yes.
So we know that R is equal to 0.0821, and that's ATM liters per moles Kelvin. So what would we have to do in this circumstance? First thing that we need to do.
Do you need to find the enthalpy?
Do I need to find the enthalpy?
Well, delta H is heat, right?
Yep.
You convert the units so that it aligns with the R.
Okay. Oh, and they also give us the other R. So this is the conversion from the R into liters. units per second. So we could actually use this as well. So we have it in joules. I didn't even see that there. I don't even need my R here. Okay, so then what would I need to do? So I need to change the units. So what am I going to change in this case?
So pressure is in atmospheres and then temperature in Kelvin.
Okay, but here the pressure is going to cancel out, right? So they're going to be unitless.
Okay, well, never mind then.
Yeah. So, but I do need to change this to Kelvin because I know that my R is in Kelvin, right? So then how would I change this to Kelvin? Do you guys remember?
273.15.
Okay. Okay, so then we would just plug it in. Our T1 is 1 over 298.15 minus 1 over 323.15 this guy's 8.31 joules per moles Kelvin. That's both Kelvin. And that's going to equal, and you're going to see this equation again, so I make sure I'm familiar with it. 92 over 24. What do you guys get? So delta H. So we get side is equal to 1.34. This is 298.5 So divided by 0.31. And then we inverse times 1.34. Okay, so it's going to equal to 42.9 kilojoules per mole for your heat of vaporization based upon the data that you collected. Okay, piece of cake?
I'd say so, yeah.
Just plug and chug, right?
Yep.
Okay, clear. Okay, a couple of things that I want to point out here. So when we're talking about that energy, the heat of vaporization and the heat of fusion, fusion is, again, melting, right? So that's basically going from, if we go from a solid to a gas, right? So a solid to a gas is called sublimation. So the heat of sublimation is going to be equal to the heat of melting plus the heat of vaporization added together, okay? And so do you guys remember, again, when we were talking about heat, thermal chemistry, intrinsic functions where, you know, it's just, it doesn't matter how you get there, it just matters that you get there. And so you could either get there in one step, that's representing just going from sublimation, or you can get there by 2 steps, and they should be equal. The amount of energy that it takes to get there should be exactly the same. Does that make sense? So the heat going from sublimation, just from sublimation, from solid to a gas, is going to be equal to going there in steps. First, going from a solid to liquid, and then from a liquid to gas. They're going to be equal to each other. Okay? Okay, good. So heating cooling curves, right? Heating cooling curves, again, you're going to be using that heat is equal to, do you guys remember MCAT? MC delta T, where M is the mass, C is the specific heat capacity, and T is the change in temperature that you're going to. Okay, now it's also going to be, when we're talking about the heat and cooling curves, you're also going to be taking into consideration the enthalpy, right? So when we look at this heat and cooling curves, this here is going to represent the amount of heat, and it's just the state that you're going through. So if we're going from 10 degrees to 0 degrees, and we're talking about water, let's say we're talking about water in this case, right? So if we're going from ice to 0 degrees, what happens at 0 degrees with water?
It melts.
Okay.
Or stays the same for a while.
Okay, so if we go below 0 degrees, is it melting or is it freezing?
Freezing.
Okay, so if it's below, so it's freezing, right? So when this stage would be equal to M, C, and that would be the heat capacity of ice, because the heat capacity of ice is different than water, delta T. Okay, at this blue line, because you have to have energy to kind of get over the hump, right? So if you guys think about it, if you're pushing a vehicle over a hill, right? So you need that energy to get it up and over the hill, because like if you're at the top part, you have to get enough energy to kind of push it over. So you're gonna need a little bit more energy to get it over. So this line here is gonna be represented by our enthalpy. So this here would be the delta H. And then we're going from an ice to a liquid. So that would be fusion. Okay, the delta H of fusion there. Okay. And then this part here is also going to be Q, and that's going to be MC, and this is going to be of water, or H2O, water, in the liquid form. Delta T. Okay, and then that's where we're going from 0 to 100 degrees. This here, this is going to be your delta H of vaporization. And then this guy is going to be where Q equals MC and this would be of steam or vapor, delta T, okay? And so if we're looking at this and we wanted to find out how much energy it takes to go from something that was at minus 10 degrees to something that was at 110 degrees. Oops. So then we'd look at the Q that's going from minus 10 to 110. That's going to be equal to the sum of each of the individual parts. So it would be, we'll call this ice. We'll call this water. And we'll call this one gas. So it'll be Q ice plus M delta H sorry, should be N delta H. N delta H fusion plus Q water plus water, Q vape. Oh, sorry, got carried away. Should be N delta vape plus Q steam. Okay, and so that's going to give us our value, the total energy for this process. So it's kind of like a step. Q ice right here, the N delta fusion. Q water, it takes us over, the N delta vape. And then Q steam or Q gas. Should just be consistent there. Make sense?
I think so, yeah.
Cassie?
Yeah.
Yeah? Okay.
What? Okay. What? I'm looking at the Q total.
Yep.
N is coming from where?
N is the number of moles.
Okay, because that's where I was like, wait, where's
Yeah.
N? Where did we get that one? Because I remember M. I remember the MCAT.
Yep. Number of moles.
Okay. For that
And
specific part, right?
no, it would be for the entire system. So it should be, if you're talking about water, it's the number of moles of water you have.
Of water. Oh, okay. Okay.
And then M equals the mass of the water. Now, it's important that you pay attention to the units that you're given, because sometimes people will make things easier for you, right? By just making it in terms of the mass. They'll give you the mass. They'll give you the enthalpy in terms of mass instead of moles. Okay, so it's going to be important that you pay attention to that as well too. Okay. Are you with me? I'm gonna have to fix a slide real quick.
And the specific heat for vapor can change, right, depending upon what type of vapor you're dealing with?
Yes,
Right.
yes, because
okay. Just like anything else, specific heat will change with each. Okay, I just want to make sure.
Okay. Okay, let's see.
And just like before, you'll give us those values in like a table and stuff if necessary.
Yep. So let me give you an example.
Yay.
Okay. So calculate the total energy required to convert 135 grams of water from 15 degrees Celsius to 120 degrees Celsius. The heat of calculation, the heat calculation for the change in temperature is Q equals MC delta T. That should be a capital T. Fix that real quick. We don't mistake it for time. The heat calculation for the change in state is Q equals N delta H. So specific capacity for water is in solid form is 2.09 joules per degree Celsius grams. Liquid state is 4.184 joules degrees Celsius grams, and gas state is 1.84 joules degrees Celsius grams in the gas state. The heat of fusion is for water is 6.01 kilojoules per mole. The heat of vaporization is 44.01 kilojoules per mole. And if you guys remember, we did that calculation, we got 42. So we weren't too far off. Okay, so what are we going to do?
We're going to convert everything.
Are you going to convert everything?
Not everything, but...
The first thing that I would always do is draw the curve because it makes it so much easier if you have the curve there, right?
Okay.
So, okay, so I know that water freezes at what temperature?
100.
Freezes.
0.
So we know it's 0 degrees Celsius. And it boils at what temperature?
$100.
Okay. Okay. Okay, so I know that I'm starting off at negative 15 because it tells me 0.0. And I'm going all the way up to 120. Okay, so now I'm going to draw my curve. So my start is there. I go up to 0 degrees. I know that that's a transitional point. Then I go up from 0 to 100. That's another transitional point. Then I go up to 120. Okay. So I know that this is going to be Q equals N, and I don't know what to use for delta. I'll draw it in here. H.
Because that's your change of state, right? That's why
That's
you
right.
want H instead of T.
That's right.
So then this one would be Q equals M delta H.
So this one here is going to be Q equals N and that's vape. We know that this guy is going to be Q equals MC. And we know that's going to be ice. And here, the T is going to be from 15 degrees to 0 degrees. So our 0 minus 15. Then we know that this one is going to be Q is equal to MC. I got right in liquid. And then we're going from 0 degrees to 100 degrees. So it's 100 minus 0. And then we have the last one, which is going to be Q equals M times C gas. And that's going to go from 120 minus 100. Okay. And where this guy represents the delta T for that transition, delta T for this transition, and delta T for this transition. Okay. Does that make sense?
I think so, yeah.
Okay. So then when we solve the problem, Q total. We're going to call this Q ice, Q liquid, and Q gas. Oops. So it's going to be Q ice plus, we'll call this Q fuse plus Q lick plus Q vape plus Q gas. Okay, Piece of cake.
So you just do the forward progression, getting every state and every temperature, like every, right?
Yep, that's correct.
Okay.
And then if we were going the opposite way, if we're going from a high temperature going down to a low temperature, you would just
You'd subtract them.
That's right. You, and so you'd end up with a negative number in that case. So, okay. Questions, concerns, Cash. Okay, good. Let's see. I'm actually gonna stop here, and then we'll continue on the phase diagram on Wednesday. Which means I got to extend your homework one more time. But Wednesday we're gonna do phase diagrams, and we're gonna do colligative properties. Okay, so mole fractions and stuff like that. Okay.
Okay.
So chapter 11.
That doesn't sound complex at all.
It's not. You've already done it already, whether you realize it or not. It's actually, from here on out, you're going to be putting pieces together, really, except for when we get to equilibrium. Equilibrium is kind of new, but it takes an old concept, but you're going to get a little more explanation.
Well, hopefully it's an older concept that I mastered.
Okay. Okay, so I will see you guys on Wednesday then. Okay.
Okay.
Oh, there is going to be a lab. I just don't have it up yet. There's going to be a lab today. It's actually going to be the Kinetics Lab. So I just got to import it into your system. So.
Okay, so we're meeting up today for lab.
Yeah, we'll be meeting up today for lab. Actually, let's just say on Wednesday. We'll do it Wednesday, and then we'll do a double because both of them are kind of. One of them, it's a long lab, but it's short. You know, there's going to be time points where you just got to take it. You know what I'm saying?
Yeah.
Yeah. So it's going to be beyond the time point that you're doing. And it's going to be important that you take images at those time points because that's the only way that you're going to be able to compare. And don't change your settings when you take those images. You know.
So
do you understand what I'm saying? What was that?
Lab is going to be on Wednesday instead.
On Wednesday. Yeah. On Wednesday, we'll do a double.
Okay.
Okay. Okay. Sounds good?
Yep.
Okay. So then I'll talk to you guys. Because like I said, one of them, both labs are going to be quick labs. But one of them is just a lot of time points. That's not a lot, but long, lengthy time points. So it'll be like, you take a picture an hour, then you take another picture another hour later, then take another picture 2 hours later. So.
Can I set up an office hours time for that one too?
Yeah, you can. Yep.
Okay.
Yep, on Thursday. Yep.
Okay, cool.
Okay. Okay. Questions, concerns, Cashola?
No.
If I had it, Dr. Henry, you'd be the first one.
Okay, that's good to know. It makes me feel better already. Okay. So I will see you guys on Wednesday. You have a good day.